Any logistical issues we have to start with before we begin? Are we okay, Vidal? Okay. I think we're okay. So we'll start a little early. We have a whole series of excellent keynote speakers. The only slight change you may have noticed if you registered quite a while ago is that Tom Carl unfortunately had to cancel his talk because he was essentially told by his NOAA bosses that he had to clear this calendar this week for some very important meetings up on the Hill. But we didn't lose much. In fact, we probably gained maybe a little bit in terms of the person who's going to substitute for Tom. Susan Solomon is going to break away from the Breckenridge meeting and join us, so I'm sure that will be just as stimulating. But our first leadoff speaker, and he's always stimulating, is Guy Brasseur, my fellow lab director in ISIL, the Earth, Sun, and Systems Laboratory, and he's going to talk about obviously chemistry, but also I think climate issues, and talk to us, hopefully stimulating in terms of the kinds of observations we need in the future. So Guy?
Thank you very much, Roger, and I'm really pleased to work with you here at NCAR. You're a wonderful colleague and a wonderful friend, and thank you for the invitation. So what I would like to do today is not talk too much about observational system, but try to put a bit of a framework around which a number of projects could be developing, and they are related to Earth system observation and Earth system modeling. But I'd like to highlight a few challenges that we have to understand the future of our planet. So first of all, if we look at the disasters that humankind is facing, hydrometeorological events represent perhaps 90% of those, 70% of the casualties, and 75% of economic loss. And you see windstorm, you see flooding, you see drought, and of course, related damages associated to them. And so today, as we look at the planet, and as we look at what happens at different time scale and spatial scale, we have to deal with a large number of issues that are highlighted here. Hail and lightning, tornadoes, tropical cyclones, air pollution, drought, flood, windstorms, ice storms, and so on. And you can see that even at the international level, the UN, through a climate change program or stratospheric ozone depletion program, severe weather program, long-term or long-range air pollution program, are trying to address these issues. So what are the challenges, and what have the challenges been in the past, and how historically have we evolved? And I'd like to give you a bit of a historical perspective, then to move towards the present and the future. First of all, perhaps the first challenge for our community has been really to predict weather. And after Newton discovered its fundamental law of the physical system, and after people like Dregnes in Norway identified the possibility of applying this general law to fluid dynamics, the idea came that probably weather can be predicted just like any other system. And of course, that requires solving relatively complex nonlinear equations. And it was done in a first attempt by Richardson, who was an ambulance driver during World War I in France. And he tried from a poorly known initial condition, to predict the weather by solving the equation numerically, but by hand. And of course, he realized immediately that this could perhaps become possible in an operational way if you had sufficient number of people, maybe all sitting in a large theater, solving a piece of the equation, giving the sheet to the neighbor who would continue the calculation. It was a human computer in a very parallel fashion. Well, the forecast failed completely, and in fact, it was in the US then, after World War II, that with the first computer that was available in Princeton, the ENIAC computer, that a meteorologist and a mathematician worked together, Czerny and von Neumann, and really made the first successful weather prediction. And of course, things have improved dramatically from there, basically because of enhanced observation, the development of data assimilation technique, for example. This is von Neumann and Czerny in front of the first computer, and you can see that computer rooms have changed quite a bit since this first attempt. But of course, from these simple models with just a few levels to much more detailed system, global forecast, non-hydrostatic model, and finally, ensemble model where the uncertainty in the analysis is taken into account to lead finally to not only a deterministic forecast, but also an ensemble of results and some uncertainty. The field has evolved tremendously. And I think, in a way, we have addressed to a large extent this first challenge, but there remain a lot of problems to be addressed, in particular dealing with the physics in the problem, in the system, and also the need for observations to reduce basically error in the analysis that we have to face with. And of course, we see here how improvement has been reached over the years. This is the ECMWF prediction skill. And of course, we should also notice here that as we move in time and do relatively well in variables like the 400 millibar height or maybe the potential vorticity, we're still doing a very poor job in terms of precipitation forecast. And I think a lot of effort is going to be on precipitation forecast, water cycle, cloudiness, hydrological aspect of the meteorological system. So one point, of course, that is important here is the tropical processes, and in particular how they affect the global dynamics. And you can see here the importance of scale interaction in all that, requiring, of course, an adequate strategy for observation of the system. You have a number of processes at the synoptic scale with time scale of days, but then they have an impact on longer time scale processes, going all the way to ENSO, quasi-binary oscillation. And how do we really address and try to make progress in understanding this interaction between scale is probably one of the major challenges that we're facing today. Then we move to the second grand challenge that the community had to deal with, and this is the prediction of the climate system and climate change. And we know also from the 19th century that, yes, CO2 is a greenhouse gas. It contributes to what was called the glass ball effect that Fourier introduced in 1824. And Arrhenius, the Swedish scientist Arrhenius, predicted that if we doubled CO2 in the atmosphere, we would probably enhance the temperature of the planet by 5 degrees, which, by the way, was not such a bad prediction at that time. But of course, taking advantage of the work done by the meteorology community, models could be developed for the atmosphere, GCMs first, and the community, the atmospheric community, realized that in order to better predict climate change, you needed to couple these models with the ocean, which is, of course, a major driver in climate change. And so those two communities had to start working together and build, in the beginning of the 90s, those coupled atmosphere-ocean model with some representation of the sea ice. Since then, of course, a number of new processes came up as being important in the climate system. The role of aerosols in addition to the role of greenhouse gases. First, the sulfate aerosols, but also other types of particles. The link with the carbon cycle became recognized as important. And today, of course, the connection with the chemistry of the atmosphere is also seen as important. And you see, of course, an increase in the complexity of these models, but not only in the complexity of the model themselves, but in the organization around these models, the need to bring together specialists from different disciplines around the problem that the planet is facing and that we will have to deal with in the next years. And in fact, if you if you look at some of the accomplishments in atmospheric chemistry, for example, Chapman and the theory of stratospheric ozone, Crutzen, the theory of ozone depletion in relation to human activities, the photochemistry of smog, and the work of Hagen Smith in Los Angeles to explain the smog. And then, more generally, the role of the atmosphere as an oxidizing medium that basically has the capability of destroying a number of gases or compounds that are emitted at the surface, including pollutants. Looking at the ocean as a component of the Earth system, a lot of progress have been made in the recent decades. The understanding of the ocean circulation and the conveyor belt, the thermohaline circulation, the role of the ocean as a biological pump, and finally the development, especially at GFDL, of ocean general circulation models that are the basis, one of the bases of climate models. The role of the biosphere in the Earth system was highlighted, and in particular, the need to recognize that the Earth is not a dead body, but hosts life, and life is key in the evolution of the Earth. And the Russian scientist, ecologist Vernadsky made this claim at the beginning of the 20th century. Then you had a number of important issues, the vegetation albedo feedback, and therefore the possibility of having several states, several equilibrium states in the climate system by Charney, the role of CO2, the cycle, the missing thing that existed. We couldn't explain really the distribution of CO2, and today this remains an important problem. I know that a number of people, and in particular the Gulf Stream, was used to try to better understand the distribution of CO2 and hence understand the changes at the surface. And so the role of the biosphere in controlling the chemical composition of the atmosphere, and also the importance of wildfires for the Earth system, a problem that's not discussed in great detail, but is in fact important not only for the chemistry of the atmosphere, but also for the fate of ecosystems. Now, the conceptual framework that we have been using to understand this, and to, in particular, to look at how humans affect the system is really shown here. There are a number of human practices and human action that impact the atmosphere, the terrestrial ecosystem, the ocean, the hydrosphere, and that has been the philosophy that we have been using. And you will see in a minute that this view is changing quite dramatically at the moment. But this is, for example, be used by IPCC to look at the results of human forcing on, say, the temperature, which is shown here, based on a scenario for emissions of CO2 and other greenhouse gases, showing here that by 2100, the mean temperature would be about 3 degrees higher, but some differences with latitude and depending if you're on the continent, on the ocean. And these models have been also, for example, projecting changes in precipitation with much less certainty and a lot of differences between the models. But this has been basically the approach. And if you look at the advances that have been made over the last decade, there's been quite a few of them. We better understand the drivers of the climate change. We better understand how to parameterize some of the processes, in particular, some of the parameterization of scale interaction, although there is still a lot to do in this area. We better understand the presence of feedback and systemic interaction of the system. We've improved dramatically our data set, and we start thinking of linking the natural processes and the human processes. But recently, the direction of the research has dramatically changed. And you see here this boat taking a U-turn, basically. The question was really in the past, is anthropogenic climate change really occurring? Do we see it? And I think IPCC has responded very clearly to this question. And so now the question evolves, and perhaps is, what will be the impact of those human-driven climate changes on the coupled human and natural system? And this, of course, required probably very new approaches, new science capability, new collaboration with other partners in the field. Because if you really think about it, major planetary issues include not only the mean temperature, or even the precipitation. But more specific, or more generally, all the problem of the energy, the carbon, the alternative sources of energy, the problem of water availability and water quality, the problem of food availability for the planet, the impacts for people, for society of high-impact weather events, air quality. If you go to Asia, you'll see what I'm talking about. And then the impacts of all that on human health. Importance of urbanization, population migration, and at the end, you have to deal with issues like poverty and education. And so, in a way, we have to adapt our tools. We have to better understand interactions and feedbacks in the system. They're very complicated to quantify. We also need to develop integrated regional studies to assess the two-way coupling between the biophysical system and the natural or social system, and do that at different scales. So it's a huge task, and that brings us to the third grand challenge today, which I think is quite new, and it's to understand the Earth as a complex, nonlinear interactive system. And of course, a number of people you show here, like Ed Lawrence in meteorology, or Jim Lovelock in biogeochemistry, Beth Bolin in climate science, and Roger Revell, have highlighted the importance of these interactions in the system, and the fact that a little perturbation could be enhanced dramatically through them and lead and bring basically the planetary system to a different type of equilibrium. So we have to look at the Earth as a system that includes the atmosphere with its dynamics, its chemistry, its photochemistry, aerosols, and so on. We have to look at the ocean with its circulation and its marine biospheric system. We have to look at the land surface with processes at different scales, the cryosphere both on the ocean and on land. And finally, in the middle, we have to look at the human system as a driver, a receptor, and sometimes a facilitator of some interactions between different processes. And of course, it's not a uniform system. We have to realize that the Earth is not uniform. You have a number of hotspots in which a number of important processes could develop. The instability or the collapse of the Amazon system, it might be relatively regional, but it will have a major impact on the global carbon cycle and therefore on the global climate system. We know that ENSO has teleconnection associated with it. We know that if we have methane outbursts in the Siberian regions, we could change very much the greenhouse forcing, and that's a global problem. So against here, those hotspots are relatively localized, but they might have cross-scale interactions and finally impact on the global system. And so the concept that I described earlier today needs probably to be somewhat revisited. And rather than talking about the impact of human actions on the natural system, we also have to look at how the natural system affect human welfare through the changes in providing goods and services, environmental goods and services, but also providing a number of issues like climate change or air pollution that will affect human welfare, and that will have a feedback at the end on the natural system. So we have to look at all of this, and probably the way, from the modeling point of view here, but it should be the case also on the observational side, to really try to link together these communities that deals with natural, or let's say physical model, chemical model, biological models, and socioeconomic models. And this is a major challenge for the future, because now we're talking about bringing communities that are traditionally very quantitative in the way they're approaching, and also looking at the generalization of the problems, and other communities which are much more qualitative in the way they're approaching the problem, and also looking more at regional and local issues. So there is a need for a new way of doing modeling, but there is also a need of a new way to approach climate observation. And perhaps one of the big issues in the climate problem today is this imperative to build an observing and information system to better plan for the future. And a climate information system includes a number of components: observation, analysis, assimilation, attribution, assessment, prediction, and then decision making. And if we look at what we have, certainly we have a good start. We have atmospheric observation all over the world. We have ocean observation. We have space observations. But they remain very specific to our disciplines. And perhaps, and this is for you to discuss more than for me, the challenge is to create a whole system view and to really look at a system of the 21st century as, taking here a slide of Tom Carl, that will bring together the information from the different components of the Earth system and also include the different time scales. ECMWF has started doing that. This is not a very visible graph, but basically what you see on the left are all the kind of observations that are available, dealing with the atmosphere, the ocean, land surface, solid Earth. And on the right, you see basically the problem: disaster, health, industry, water, climate, weather, ecosystem, agriculture, biodiversity. And our role as scientists is in the middle to develop these toolboxes, observational tools, modeling tools that will basically use this observation to provide societally important, relevant information on these issues that are listed there: weather, water, climate, biodiversity, etc. And that might be a challenge for us. Now, what I would like to do is to highlight a few examples of what I think are Earth system questions. And you will see they're very diverse, but they're all very fascinating. First of all, when you talk about climate today, you cannot isolate it as either a meteorological problem or an oceanographic problem. Climate, of course, is linked to greenhouse gases, to aerosols, but also to gas phase chemistry, to ecosystem and vegetation dynamics, and to the water system, the hydrological cycle, which is affected by human activities like damming, irrigation, urbanization, and so on. And then you see a large number of connections between these boxes that are basically the topic of science research. We need to understand those interactions, and then we need to see how they will be affected by human emissions, by fire, by land use changes, by damming, irrigation, and so on. And so this is maybe the general context. And so let's look at a number of questions. One of them certainly is to understand the polar feedbacks. We know that the polar region is changing at a large rate. And in fact, this is here the model developed at Los Alamos, the model also we're using here at NCAR and CCSM, that really tries to predict the evolution of the ice sheet. And you see it's getting bluer and bluer, meaning that basically the thickness of the ice is reducing. And in fact, whoops, sorry, if you look here at three times in the next century, basically the present, then around 2015 and 2050, you see an abrupt reduction in the ice sheet. And of course, what is interesting to see is these models do not show a gradual decrease, but an abrupt decrease. And the time of this abrupt decrease can really change from model realization to model realization. So it's not a very, the fact that it's here declining around 2030, it's not a very strong prediction. But of course, as this is happening, we have to look at the consequence of this. And you see here, okay, Arctic warming, there will be a lot of issues that will happen. The soil will change, the permafrost will disappear, the microbial activities in soil will increase, the wetlands will expand, and that will lead to probably enhanced emissions of CO2, enhanced emission of methane, perhaps modification of the nitrogen cycle, and runoff also, of course, that could impact the ocean circulation, certainly the emissions of greenhouse gases, and have perhaps some positive feedbacks. But these are very poorly quantified. It could also be negative. So let's go to a second question, which is to assess the role of the coupled carbon and even nitrogen cycle in the climate system. In fact, if you look at the emissions of the CO2 fluxes between 1850 and roughly present, you see a dramatic evolution. The first curve to look at is the fossil fuel emissions that have increased, but the Earth has responded to that. First of all, of course, we should also take into account the land use changes, but then this CO2 has been partly retained in the atmosphere, it's been partly absorbed by the ocean, and has been partly taken over up by land, and of course with very, very high year-to-year variation depending on the weather and the climate, and showing how basically here a feedback between the two could happen. So how is this going to evolve in the future as more CO2 is released? How is the atmosphere going? How much is the atmosphere going to retain? How much will the ocean be able to capture? And how is land and the vegetation going to evolve? Will there be a positive feedback in the system? This is here one model calculation that shows you basically that if climate changes, because the temperature increase and the hydrological cycle changes, the emission of CO2 from the biosphere or from the ocean, or at least the exchanges, will change because of the change in climate. And in fact, everything that is brown is an additional release of CO2, of carbon, to the atmosphere. Everything that is in blue is an uptake, an additional uptake of carbon from the atmosphere. And you can see that in particular in the tropics, there will be additional release of CO2 in the future because of some damage and perhaps partial disappearance of the tropical forest associated with the dryness, the more drought occurring in this region, and reducing the vegetation, the size, the volume of the vegetation. There might also be effect due to changes in the ocean circulation. In the Siberian regions where precipitation are expected to be stronger, you might have a development of the vegetation and therefore a negative feedback in this region. But overall, the models seem to indicate a positive feedback between the carbon cycle and basically the climate system. I'd like to go to the third question, which is to quantify the potential positive climate feedback associated with methane. And the first point is to remember that methane is produced essentially in wetlands, lakes, and other oxygen-deficient ecosystem. It's partly oxidized, but some of it gets to the atmosphere. And this emission is very temperature dependent. And so if climate changes, we could change very dramatically the emission of methane from wetlands. For example, Walter and Hyman have derived that every time you warm the surface, the land, by 1 degree, the emission of methane by wetlands is increasing by 20%. That's a very high sensitivity. In addition to that, we have large pools of methane called methane hydrates that are locked in ocean and permafrost. And of course, if the Arctic melts and if the temperature raises, we could have the release of additional methane in quite large quantities. Here are the location that we know about of those methane clatrates that are either in the bottom of the ocean or under the permafrost. And they have a certain stability. You see here the stability curve. And if you were to change this curve and moving it to higher, warmer temperature, you could create some unstable zone and release of methane. And so if you double CO2 in your models, you can estimate from different IPCC models here the probability that you have to release some of the methane from those large quantity that are kind of maintained at the bottom of the ocean or under the permafrost. So we could have an increase in methane emission, and we know that methane is a very powerful greenhouse gas. It's about 30 times, I think, more powerful than CO2. So we have a number of challenges here. Better quantify the different processes affecting the global carbon cycle, study biogeochemistry and land-atmosphere interface, couple those biogeochemical issue with the hydrological cycle, human perturbation, and climate change. And then we have, of course, to couple the carbon cycle with other biogeochemical cycle. You show quickly two slides that I didn't describe on the connection with the nitrogen cycle. Nitrogen is completely out of balance because of food production, but nitrogen is a fertilizer and affects, therefore, the carbon cycle. And then we have to consider the possible positive methane climate feedback in the future. Going to question 4, the role of aerosol. I think that's a major issue and not a very well understood and certainly not a very well modeled issue in the climate models. So aerosols are complex. You have different types of aerosols. You have different sizes of aerosol. You have different mixing states of aerosols, but you see that they produce by fires, by human activities, volcanic eruption. They also release when dust by the wind as dust or sea salt, for example. And so we have now a number of models that show, for example, the global distribution of different types of aerosols, and you can see again that it's not a uniform issue, and you see very much dust coming from the desert, you see the sea salt, then you see the sulfate. More and more important in the discussion now are the organic aerosol, and I'll try to say a word about that in a second. So aerosol-climate interaction are important. They shading the surface from solar radiation. They're also heating the atmosphere, have an impact, therefore, on the whole climate system. And of course, more and more we need to understand not only the direct effect of these aerosols, but also the impact on the cloud system and how they can modify, for example, the albedo, the lifetime of the clouds, and therefore the what we call now the indirect effect, the indirect forcing of aerosol through clouds. And I think this remains a very, very open issue that requires a lot of observations, observation of cloud processes in particular, and that's probably still on the table for discussion for some time. I mentioned the secondary organic aerosols. They are really produced from emissions of a number of organic gas phase compounds, like terpenes, for example. Some aromatic, some are naturally produced, some are produced as a result of human activities. They undergo an oxidation process that is complex. The organic chemistry of the atmosphere is complex. But finally, through nucleation or condensation, also through cloud processes, they end up being organic particles. And these are very often the most abundant particle. They roll then on of course, my phone is always ringing at the wrong time. I'm going to turn it off immediately. These organic compounds remain a bit of a mystery today because they seem to be the most abundant. They seem to be very much of biological origin. But on the other hand, they seem to be most abundant where human activity has a big impact. And so aerosol biosphere interactions are important. Not only because of the organic aerosols that relate basically the terrestrial biosphere to the meteorological system, but also because of dust, because of nitrates particles, which affect the marine biosphere, the terrestrial biosphere, and therefore the carbon cycle and even the sulfur cycle. So here is a sketch that shows you basically how biogenic VOC affects finally clouds and climate, or at least could affect cloud and climate. This is a slide from Alex Günther, but these issues remain very questionable, uncertain, and require certainly a lot of field information, field observation and information to better understand what's happening. So again, we have a number of challenges. We need to address fundamental uncertainty in our understanding of aerosol microphysics, chemical composition of aerosol, aerosol-cloud interaction, indirect cloud effect. Particularly, the role of organic aerosol needs to be looked at. We need to develop the field campaign, the laboratory experiment, and the physical model that kind of help understanding how these processes operate and how they impact the climate system, and look not only at their local effect, but even at the impact on the biosphere, on the ocean, on the carbon cycle, and so on. Question 5, what is the effect of climate change on air quality? And here again, if we look at atmospheric chemistry, we have to deal with different scales. Just like in meteorology, we have local processes, we have regional processes, we have global processes. And you see there the climate shown, but of course, the climate issue is related very much to a number of issues like acid rain, smog, air pollution, ozone layer, and biogeochemical cycle. And so if you look at air pollution, we believe, the chemistry community believe that air pollution events or regional ozone pollution, for example, will increase as the temperature increases. Here you see the probability of air pollution events in 3 areas, including Los Angeles, and as a function of temperature, but also because of possible weaker circulation and stagnant air. Now, it's interesting to see that according to the World Health Organization, about 865,000 people die prematurely from outdoor air pollution in the world. I put the value here in Brazil because I just showed this slide in Brazil. But what is interesting is to see that if you have 1 degree Kelvin increase due to CO2, for example, you will increase the number of premature death worldwide by probably about 20,000 people, which is more than the number of deaths that you would expect from enhanced storminess due to climate change. So as we look at the impact of climate change, certainly the issue of air pollution is also important. In reality, I don't want to get too much into the feedbacks, but a lot of these emissions of natural compounds that are the reason of all these ozone and aerosol effect are very temperature dependent, and you can see here, for example, the emission of isoprene, very temperature dependent, so climate change would really change the nature of the chemistry of the atmosphere. Another important impact on the system, as I said, will be fires, biomass burning. Remember that about 50% of the carbon monoxide emission is from biomass burning, NOx 21%, methane even 8%. Now, if we increase biomass burning in a warmer climate, I mean, when we had the heat wave in Europe in 2003, there were a tremendous number of fires in Portugal, in other regions of Eastern Europe. That would change the CO2 balance, but also certainly the pollution. So there is a need to follow how the air quality evolves, for example, through an integrated observation system. And that includes, of course, satellites, aircraft, ships, ground station. It also includes the need for agencies to work together. I took again this from Daniel Jacob here at Harvard, who said, what is the observing system for atmospheric composition that we need in 2050? And he claims satellite, geostationary satellite in particular, are important to follow the evolution of the pollution system. You need surface side on land and surface side on the ocean, which we call ships, to look at long-term trends, surface fluxes, process information. We need also observation from aircraft, and in particular, perhaps with the possibility, in addition to planes like the G5, having robotic aircraft that will provide information on processes, but also on the fluxes. And finally, we need models that are adaptive, Earth system models that will assimilate data, perhaps do inversion to understand from the observation of concentration what the fluxes and the emissions are, to better understand and to better predict the system. So there is a major issue here for the chemistry community and the climate community is the development of this type of network. Challenges for the future. Better quantify the role of the oxidizing power of the atmosphere, and so which means basically understanding the chemistry of the troposphere, better determine which processes climate and how climate change could affect air quality in the future, better assess the role of the biosphere and also the upper troposphere and lower stratosphere, the UTLS. It's a very, very important region because in relation to the climate system, but also very important to understand atmospheric chemistry. So we need to understand all that if we want to understand the chemistry-climate interaction. Make full use of ground-based and space observation to understand processes and quantify the chemical budget. Let me finish now by let me just say a few words about modeling here. And this will be very brief. But as you can see, the community dealing with the atmosphere, the community dealing with the ocean, the community dealing with the land and the terrestrial biosphere, the community dealing with the hydrological cycle have been working increasingly together. And the challenge here today is to move from what I call here climate weather models, which have been tremendously important and will remain important for the decade ahead, to really go towards Earth system models that unified all these models, put at the center the water system, but also the carbon cycle and the biogeochemical system. Put together observation coming from different sources, including space observation, so that finally we have a predictive Earth system modeling system that will help us predicting possible natural hazard. These models requires large computer capability. In the 90s, we were talking about megaflops. Now we're close to petaflops, and very soon we'll have to deal with exaflops type of system. This is the global view. But we should not forget the importance of the regional and the local view. And I believe that as we realize the interactions between all the processes that you see on this graph, a big challenge, just like the meteorologist has the challenge of developing weather forecast model, 30, 40 years ago, we now have a challenge of developing a knowledge system that has a regional focus, that is there to inform society about options regarding mitigation and adaptation strategy in response to climate change. And I think this is a big challenge for the community so that governments, industry, and so on can use such type of systems. And again, I'm not talking about modeling here. I'm talking about knowledge system. So a strong observational component attached to it. They can use this system to make informed decisions about how to address the problem that they're going to face. Let me now finish my presentation by what I think are a few new emphases. One of them is the role of geoengineering. You heard much more and more talking about that. And the question is, can we fix the climate or the environmental problem that we're facing? A number of geoengineering strategies have been proposed. Space mirror in space. Mirror in space. High-altitude sulfur injection. Critson has been proposing this. Just let's put the equivalent of a volcano in the stratosphere. Seeding the clouds, the stratocumulus clouds, making them brighter so that they reflect better and cool the surface. Sequestration of CO2, iron fertilization. Now, I'm not saying that we should do that. We're not proposing to carry out geoengineering. But I think we should know what we're talking about and what could come out of those solutions. Because in 50 years from now, if all the other strategy of limiting CO2 emissions fail, the government may come to our community and say, what would happen if? And we cannot just say, oh, we never thought about this. We never discussed this. We don't know. We have to know. We have to look. It's an interesting intellectual problem. But it's not an easy problem. This is an example here. You see here the prediction of the temperature for, let's say, business as usual, one of the scenario. And this is here in yellow, brownish, the commitment. So in other words, if you didn't release CO2 anymore in the atmosphere, this is where you would be. So perhaps in 2020, we will be asked to go back from this increasing temperature situation to the commitment curve. What should we do to do that? Well, we should add about half a Pinatubo eruption per year in the atmosphere to bring it back to the commitment curve. I don't know if you realize what commitment that is, what challenge that would be. The amount of course, this was a supervolcano. We would have to put so much sulfur in the atmosphere that it would probably be very difficult to do, and certainly, it would require a lot of money to do that. In addition, even if you meet the mean temperature, you don't know what you're doing exactly at the regional level, and you could have some disturbances, even though you're back on this curve, that would occur in certain regions of the world. But second emphasis, I think, for the science is really to move from these long-term scenario simulation projection that we've been doing to try to predict the climate change at a shorter time scale, like 10, 20 years. And that's a big scientific problem, because you could ask yourself, is there predictability in such a problem? Well, you can see here an attempt that has been made by running a model, different realization and an ensemble, trying to simulate here the thermohaline circulation in the Atlantic. And you can see here, if you take, say, 10 years, that there is hope that for certain variables there will be some predictability on time scale of 10 or 20 years. But you don't see here all the realization. In particular, this graph doesn't show that some of the realization are very different from the control run. And so this is a very important but an open problem to see how much we could really do decadal prediction of climate in the future. Finally, the third emphasis is to develop the methodology that help us coupling the natural Earth system to the human system. So I said, what we have been doing up to now is to consider perturbation, look at how that would affect the system, and finally try to estimate the impact. But today, of course, we have to deal with possible feedbacks that include here a number of processes that are highly controlled by human activities. And the question is, how do we do that? How do we approach this problem? How do we include in, we're very comfortable by doing this in the natural science community. We're very uncomfortable by taking this into account, like the structure of the economy, economic growth, population changes, growth, migration, and so on, and see how that would happen. And so this is, I think, one of the major challenges. Let me come to my conclusion. You see that a lot of what I have presented here is very interdisciplinary in nature. I've been talking about the atmosphere, which itself has a lot of discipline involved. I've been talking about the ocean. I've been talking about the land. I've been talking about the human dimension. And so more and more we'll have to move to interdisciplinary approaches to answer very specific problems that society asks us to address. And so how do we organize our community to be able to provide these responses? Certainly we'll have to develop more interdisciplinary programs. What are the conditions for the success of an interdisciplinary program? Well, here's some of them. We need to start learning the language of others. We need to share concepts. We need to share languages. We need to have people collaborating, but those in particular who excel in their own field. You don't want to bring the people who failed in their field and say, oh, we're doing interdisciplinary work. They have to be good in their own discipline. We have to develop a joint proposal process. We have to allow the people who participate in this interdisciplinary program to remain active in their own field and succeed in their own field. We need to develop intellectual mutual respect. We need long-term commitment for these projects. We need good communication. We need joint location to a large extent, even though electronic communication sometimes can replace part of that. And we need shareholder participation. So that's a very different way of doing business. And that requires, I think, a lot of discussion. So today, I think this will be my last slide. The community is changing. The environment, the scientific environment is changing very much. We have started to do a lot of basic research years ago. We have looked at operational applied research. We have been trying to develop prediction, assimilating data, doing assessment. And we're moving now from this basic research further and further to providing information that is relevant to society and developing, for example, climate services. The US is going to develop a national climate service. But all that requires a broad approach. I mentioned interdisciplinarity, but I would also say that not everything will be done by modeling. We need observations. This is fundamental. We need data. We need the capability of analyzing these data. We need to put them in the models. We need to produce information and get product for society. And the only way we can do that is by working with users, decision makers, and stakeholders. This is perhaps the structure of the research, the activities around issues like climate, but also more than climate, just global environmental issue. Thank you.
Oh, thank you, Guy. I knew you had to count on you for stimulating discussion. So, does anyone have any questions? And if you do, please use the microphones. And I guess it would be also useful if you can identify yourself, since this is being recorded, or give someone else's name if you don't want to know. Yeah, go ahead and use the microphone.
Yeah, Jon Jensen, EOL. You gave a very wide-ranging talk here, but let's just say that you were focusing on prediction of severe weather 10 years from now, and you have a fixed budget, and you have three things you can spend your money on. You can spend it on better physical representation in models. You can spend it on faster computers, and you can spend it on what I would call routine observations like larger scale satellite and so on. How would you spend your money to get better at severe weather forecast 10 years from now?
Well, if you allow me to not to put all my money in one single basket, I would probably say that, money is limited, of course, and so probably you would have to put a third of the money roughly in the three pockets. I think that it's very difficult to say that, well, let's do observations and no modeling, or let's say modeling and completely forget observation. We certainly need computers to improve the resolution in the model, to improve the amount of physics we develop in the models. But if we do that alone, without having the observation as a background, it's a waste of time. So for me, as a scientist, I believe very much, and maybe as a modeler, I should say, I believe very much in the observations and the need for observations. But I also believe that the observation is only really useful if it improves your model and your predictive capability. So I would probably have a prudent process that would evolve possible and intelligent advance on the three fronts that you mentioned. Might not be exactly what you expect from me, but I don't know I could better answer that.
Bob Serafin from NCAR. Guy, what is the status now of these Earth system models with regard to the closure of the carbon cycle, and what is your prediction as to when we'll have one of these closed carbon cycle Earth system models that are actually representative of the Earth system?
A number of models in the world, perhaps 10, have been coupling a representation of the carbon cycle and the climate system, and have tried to quantify basically the feedback. I showed you one example here, but I should say that there are large differences between what the models are predicting and how they quantify the strength of this positive feedback. If you take one extreme, the British Hadley Center Met Office model, they see a large feedback. And they're probably the only one having such a large feedback. The reason is not only because of the representation of the carbon cycle, it's also because their climate model, their physical climate model, show basically a disappearance of the Amazon. It's getting very dry. The tropical forest is to a large extent disappearing. A lot of carbon is released in the atmosphere. If you take other models, like Ines Funk's model, which was basically using the NCAR model, you see about a factor of 10 less impact. So the issue is that these models exist. They are not constrained very much. They provide, at the moment, very different results. One of the reasons is that the physical climate models is behaving in different ways, but more importantly is the way the exchanges of carbon, in particular with the land biosphere and the soils, is occurring in these models. These are very simple representation of the carbon exchanges. And so at this moment, I don't think we can trust this model at all, but we can just encourage people to improve their representation of the carbon processes, in particular in soils and with the biosphere. Those people at the beginning, and just like every model at the beginning, it's a lot of uncertainty associated with them, and they will make progress in the next 10 years. We'll see what comes out at the next IPCC synthesis on this particular issue.
Johannes from the University of Idaho. Thank you for your inspiring talk. I would like to ask a question which may not be addressed by you directly. How organized are the activities of NCAR in addressing interdisciplinary issues?
Well, NCAR has put increasingly large emphasis on interdisciplinary activities. I mean, the lab that I'm running, for example, includes, under a single framework, 4 divisions, and those 4 divisions work together very much in relation, for example, to the development of Earth system models. You need a meteorologist, you need a climate scientist, you need the atmospheric chemist, you need the upper atmosphere people. They also collaborate with scientists in other labs, for example, applied mathematicians, for example, numerical people in CISL. They work also very closely with people doing experiments, both inside the lab and outside the lab. And so NCAR has now created a new program to foster, basically, enhance those connections between people in different units, in different divisions, in different labs. I believe personally that this is great but not sufficient. And this is not sufficient because the next step, and we have been discussing this a lot with NSF in the last year, is to start creating a virtual network or network of virtual centers, centers of excellence that exist all over the country, in universities in particular, national laboratories, and try to see how the experts from these different groups and disciplines can work together beyond the wall of NCAR and really try to make NCAR a virtual center, very distributed over the country with strong participation of all the groups, the universities, the centers in the country that could contribute to such intellectual activities. I read recently an interview from the former director of NIH in medical science. He was saying exactly the same thing. He said, if you want to address difficult diseases, you need interdisciplinary group of doctors, of physicians. But you cannot do that only at NIH. You have to get the whole country involved. And so NIH has to become a network of excellence in the country. I think that's what I wish NCAR would become in the next decade. It takes time to do that.
So with regard to observations, most observations are taken at ground level and over land, and 70% of the Earth's surface is covered by oceans, and a lot of the problems that you showed, they are actually in places where there is no human activity in terms of class rates, coastal environments, or the wetlands in Russia, or Siberia, tropical latitudes, few observations, and again, those that there are, they are mostly at ground. At the same time, you have the satellites, which give you a global view, but are difficult to link up in terms of any ground-based observations. So in terms of a network of sensors that could provide data on a global scale, I mean, do you see movements that at least on a US continental scale, if we just stay on the ground over terrestrial environments for the moment, there is a movement that actually there will be a data networks that can provide a link with satellites in a way that they are meaningful. And then how do you extrapolate that to the global environment if you attempt to tackle issues that are in remote environments?
Well, you saw in one of my slides, I was trying to explain that we need to develop really an Earth system, observational system, basically. And of course, that has to be global in nature. Now, we are at a time of a globalization. The economy is global, the exchanges of information between industry everywhere in the world. I think the scientific community needs to basically make an effort to become more global than ever. Now, you have in many countries a number of activities that we know very little about in the developing world. You mentioned Siberia. There are a lot of activities there, monitoring and trying to understand processes over land in particular. And these observations are not really shared. And I think really one thing that perhaps we need to be thinking about is to start networking international institutions and just become as global as the economical system is becoming. I mean, there is a lot to gain from exchanging data, from exchanging information, by exchanging students, exchanging postdocs from all this country, and try to have much more information that we could then use to feed models and data assimilation system. The meteorological community has solved that problem for a long time to do weather prediction, but in other areas, atmospheric chemistry, biogeochemistry, ecosystem, that needs to be done. Then the ocean. And of course, the ocean is another issue, but I think that requires discussion also. I'm not a specialist of that, but I know that, of course, there are some efforts to try to improve the number of data points that we get from over the ocean. I don't see anybody.
Let's thank Guy for his presentation.